So, as I said, I'm Alex Albore, and I'm presenting a joint work with Florent Teichteil, Nathalie Peyrard, and Régis Sabbadin. So also a joint work between two research institutes in Toulouse, ONERA and INRA, and we are going to talk about online replanning approach for crop fields mapping with autonomous UAVs. Why crop field mapping? It's an important tool for precision agriculture. To manage the production in crop fields, to organize the distribution of the pests, and so on and so forth. And until now, this is done by hand, basically by human annotators. Basically, the peasant goes into his field and looks at the spatial phenomena he has to map. In our case, we are going to talk about width mapping, but this technique can be applied to several different phenomena that happen in crop fields that can be mapped and for which we can represent the knowledge about the spatial distribution. So what do we want to do? We want an approach that is lightweight. So we don't want to distribute sensors all over the field. We want the approach to be autonomous. We want the tool to provide to be autonomous. So if we are using a UAV, we don't want the pilot to come with the application. We just want the UAV to be deployed on demand, so arrive there without any heavy machinery, without any offline expensive calculations. Just switch the thing on and let it fly and build the map of the phenomena we are mapping. So what's the first problem we encountered? The first problem we encounter is that we cannot do generally an exhaustive mapping. Why? Because it's expensive, first of all, and second, the field can be very large or can be in terraces. It's something expensive to do. So we're oriented toward a sampling approach, meaning observing here and there some data, and then from this data, rebuilding the whole map of the phenomena we are observing. So the first question is how to represent such knowledge about the spatial phenomena and the correlation we might have about this data. And then, as long as we want to do sampling, we want to do sampling the best way possible. I mean, we want to observe the plots in the field that will bring us as much information as possible. And here we have two criteria that are already bumping the one against the other. On one side, we want to explore, to fly as much as possible to gather a lot of data. But on the other side, we have strong constraints on battery life. So we cannot fly all the time we want. We have constraints. So the planner that generally tries to minimize the cost of the plan will try to minimize the distance flown. So how do we deal with these two criteria? For the rest of the talk, we are going to see how do we represent the knowledge about the spatial phenomena we are mapping. Okay. And we are going to call for help graphical models. Then we are going to see how do we drive UAV, a drone with automated planning. Then see some empirical evaluation, and then we will conclude. The empirical evaluation will be against existing approaches to adaptive sampling techniques for width mapping. In particular, we are going to compare against Peyrard and co-authors, a paper they did in 2013, in the context of manual mapping. They were using a greedy approach, meaning that they were selecting the plots where to sample at based on the plots that will reduce the most the uncertainty about the spatial distribution. It's a very fast approach, but it doesn't take into account the battery life, for instance. So it's not what we really want. Another approach, basically what Mathieu Bonneau did in his PhD thesis, was using a reinforcement learning to embed as well the constraints on the adaptive sampling, but this approach requires a huge offline calculation time. And we want to have a tool that can be deployed on demand, so it's still what we don't want. Our approach is oriented toward a non-greedy sampling in a Markov random field. So I think you're all familiar with what a Markov random field is. For all that interests us is a probability distribution of the spatial phenomena. So the simplest thing we found to solve this kind of problem is to separate on one side the task of selecting the sites where we are going to do the sampling, and on the other side, the planning of the sampling order. So here you can see that we have a closed loop in a typical interleaving planning and execution approach. So we have our probability distribution of the spatial phenomena represented in the Markov random field. From that, we extract the expected gains we can have from observing certain plots. So the sites that are interesting for us. The planner provides a trajectory connecting them. So a plan that is executed by the UAV that does the observations, the sensing. From this data, we update the probability distribution and so on and so forth. So how this Markov random field is updated? So here we have a probability of a vector of random variables that is driven basically by what we call Potts potential functions. The Fi and Fij functions. The Fi helps us to encode a prior we might have on the abundance class we are observing. So we are observing amount of width. So here we can say we expect to see that amount of width in this position, this site. And Fij is the correlation matrix between two sites that are nearby. So how does the width spread? You will see that we have two models of spreading for the width. Of course, the choice of this function is very important. It's very delicate because it drives the whole approach from the selecting of the sampling site to the plan. And these data are given to us by agronomists that extensively study these phenomena. So how do we choose the sampling sites? We choose them based on the expected quality gain, which is this formula that is the sum of the probability of the best variable for all the sites in the map, in our field, before and after an observation. So the gain we can expect on the final quality of the reconstructed map from an observation. I will show you just a very simple example, a fake one. I invented this data for educational purpose. So you have here the representation of our field. Let's say that the best gain we can obtain from observing are represented in red, is represented in red, in green and blue, less gain, so less interesting sites. We select n sites to sample at, which are 20 in our application. And then we call a planner that finds a path that almost joins all these sites. Why almost? Because this is not a TSP problem, it's a planning problem. We have causal effects. In particular, when we observe in one site, the expected quality gain from the neighboring sites lowers a lot. So let's say you have a cluster of points, the one close to the other, but all interesting. It suffices to observe right in the middle of the cluster to have enough gain on the quality of the final map. And then we're not interested in observing to the points that are nearby. So that's why the path passes next to the points, but not through all of them, and try to optimize the distance flown. So we said that it's a replanning-based approach. So what we do, we model this problem as a classical planning problem. We call a classical planner, thanks to the LabCat planning suite of Nir Lipovetsky and Miguel Ramirez, that we implemented as ROSE nodes, so on a robotic platform. We'll make available the code very soon. And basically produce a plan, which is a sequence of locations and expected observations. During the search, we guarantee that we don't exceed the physical constraints, the battery life, by carry on a numerical variable, just to prune out all the plants that violate these hard constraints on the battery life, in a very similar way that Fran Ivankovic and maybe Patrick and co-authors did last year, but in a much more simpler way, because this doesn't touch the heuristics, you see, no? Then the plan is executed by the UAV, but we monitor this execution. What does it mean? It means that if the quality of the reconstructed map is lower than a certain threshold, we stop and we replan from updated Markov random field. So taking into account the data gathered so far. Why? Because if we have a bad quality on the reconstructed map, it means that we are observing sites that are not informative. So that's why we stop and replan. If everything goes well, we sample on our 20 sites, then we select 20 more sites, and we continue. So you're saying that basically we are producing a partial MDP policy from every state with every call to the planner. Empirical evaluation. So we are comparing, we said, to the Peyrard and co-authors approach. It's the only one that we could use online. Qualitatively, say that we select 20 interesting sites. The planning approach finds a trajectory connecting all the sites, having in mind of minimizing the flown distance, while as the other approach is greedy, it has no look ahead. So it flies from one site to the other, following an order based on the amount of uncertainty these sites have. And from the numerical point of view, we ran some tests on a simulated environment. Next time I will show you a little video about that. So on the horizontal axis here, you have the flown distance. We put an hard limit on 4,500 meters for our planner. And you have the red and the green line that represent the two versions of the greedy approach. And we see that our planning-based approach, which is represented by the blue line, which corresponds to the data that are in the proceedings of ICAPS. The purple line, it's a new version that provides us better results based on our implementation of loopy belief propagation algorithm that we're using to update the marginals in the Markov random field, due to Sylvain Jasson and Damien Leroux. So we can see that we obtain the same quality in much less time and much less distance. This is for an isotropic model of spreading of the width, but we have a similar behavior for an isotropic model. So to conclude, we have future work to do. So we have to perform a series of real-life tests on an Aztec Firefly UAV. We have to use a more elaborate image processing module that is very simple, the one that we are using, and also think about a non-dissociated approach. This problem can be encoded as a POMDP, for instance. We have to check if this scales up or not. And then there are many other application fields, in particular in agronomy, in precision agronomy, that can use this approach of unifying a planning approach with graphical models. And I think that's all.